Okay, so for this example, we have to build a composite furnace, construct a furnace using an inside wall temperature of 1300 degrees Celsius. So maybe we are trying to melt iron or steel, and then the outside wall is 40 degrees Celsius. So there are three types of bricks available with the following properties. So the heat loss must not exceed 800 watts per square meter. So calculate the minimum thickness in meters. So how do we answer this? No? So we have an option to maybe choose brick A, brick B, or brick C. So actually this is maybe a trick question, no? Because you might think that you should use three of them. But in reality, you can use actually just one or two. No? So if you use three bricks here, you got it wrong already. No? Because you should use only two at this point. So the problem with uh, brick A, as if you imagine this, it has a very high thermal conductivity, meaning, in other words, the resistance will be quite low. No? So the more practical, or if you find actually the actual R, brick A will be the best, sorry, not the best bet, but it will be used only because the allowable temperature is 200 degrees Celsius. So it can be used until 1000 degrees. But the most practical brick that we should use should be brick B because it has the lowest thermal conductivity, meaning it might have a higher resistance, no? Because of this. Okay? So it has an allowable temperature very high as well. And that's a good or an ideal problem, an ideal property comparing this to brick C. So brick C has kind of okay thermal conductivity, and the maximum allowable temperature is very low. So let's check later if the resistance will be good for us. But we should use brick B and brick A. So we will use brick A for its maximum allowable temperature. So as it reaches 1000 degrees Celsius, we will use brick B for everything because again, this has the best resistance. So because we are trying to find the minimum wall thickness, no? So we have a minimum we want to optimize. So we have to decide properly. So a lot of times when we are designing, for example, furnaces, we are faced with this problem, and of course we should use the most practical, no, material, and usually also the highest resistance material with the highest allowable temperature. So to begin with that, we can imagine first, no, if we use three, no, three bricks for example only. um so you have the first resistance, the second resistance, and the third resistance, no? So you have 1300 here and then 40 degrees Celsius on the outside. So these are the surface temperatures, no? So you have the resistance A, resistance B, and resistance C. Okay? So you have temperatures here in between, no? So you have, let's say this is T2 and let's say this is T3. No? So if this is T1, if this is T1, this is T2, this is T3, this is T4. So what we can do here is we can find first the resistance, no, the effective resistance of each to find the the temperatures here in between, no. So we want to make sure that when we are using, let's say, brick A, it should be above or yeah, well, yeah, it should be below 1000 degrees Celsius before it goes to brick B, for example. So we also have another constraint. So the Q must not be should not be greater than 800, no? So this is the limit, no? 800 watts per square meter. Yeah. So to find the temperatures, no? You can find the temperature T2 first. Actually, this is the most optimal way to start because if you start at T3, it will be not a good idea because uh we have the maximum allowable temperature as our constraint. So we should start first with a higher temperature. So to find the temperature, no? So you have the Q is equal to delta T over R, basically. This is the simplified formula. So this Q here, we're imagining if this is a single node, so the Q here, let's say this is QA, let's say this is QA, this should be equal to QB, and this should be equal to QC. Okay? Because it passes through a single node, no? A single linear node. So we're assuming that the Q will be equal all throughout. So it should be 800, no? And we can find first T2. So you can imagine, we can just imagine for 1 square meter, no? So for 1 square meter of area, so per square meter of area, you have the Q, no? And then area is equal to delta T over R, no? So the R here, sorry, the delta T here is T1 minus T2. So we have given R, we need to find the R first, no, to be able to solve this. So to find the R, we can calculate the R first. I think I'll just write this here. So the R for RA, you can calculate this as L over KA, no? So L over KA. So we're assuming for 1 square meter of area only since the area is not given. So this will be 0.12 meters over K, so 1.5 watt per meter Kelvin, and then 1 for 1 square meter of area. Okay, so for RB, that will be applicable as well. So you have 0.2 over not 0.2, 0.07, 0.2, then 1. For RC, you have L over K as well since this is conduction, and then 0.1 and then 0.7 times 1. So you can calculate this. You have 0.12 and then 1.5. For we have 0.08, 0.08, and then 0.07, 0.07 divided by 0.2. So you have 0.35, and then you have 0.1, okay, and then 0.7. So you have 0.1428, 0.1429, no? So this is all in watts, sorry, in Kelvin per watt, no? Kelvin per watt. So the higher the resistance, the better it is as a material. So we can see that this is the best material to use, but the problem is it doesn't have that flexibility with its allowable temperature. So we should use RA until it reaches 1000 degrees, and we can use this all the way. So we don't need really RC, you know. So basically, we just remove this, no, actually. In reality, we don't need the brick C. So we will only use brick A and brick B. So this will be 40 degrees already. Okay? So to solve for T2, you can try, no, already. For only one of this, so you can imagine only one brick of brick A. You can find the temperature to be, so we have QA is equal to T1 minus T2 over R, no, RA. So to find this, no, so your Q here is 800 watts per square meter times 1, no, per 1 square meter, and then T1 is 13, and then T2 is T2. We don't know the T2, and then you have 0.08. So you can solve for T2 here. The T2 will be, let's see, I'll just do this mentally. So 13 minus 800 times 0.08. As you can see, you have 1236 degrees Celsius, no? So the problem here is this is not correct, no? So you should have at least a temperature upon reaching this point 1000 degrees, no, at most. So meaning we need to increase the thickness. But since the brick has fixed, no, so we can imagine a brick has a fixed thickness, we can increase the number of bricks, no. So this is in discrete value. You can do 2 bricks, so the 2 bricks will be 0.24 and so on. So to attain that temperature that we need, what can we assign here is instead of finding the T2, we can assign T2 here and then find the resistance needed to reach that 1000 degrees. So you can imagine 800 again, no? So I won't write the 1 anymore. So you have 113 minus 1000. So we are imagining T2 is 1000. And then we can find the RA, no? So the RA, that is minimum, okay? So I've written here the minimum requirement of the resistance to reach 1000 degrees. So to find this RA minimum, this will be can be calculated, no? So I can just do this mentally. So 300 over 800. This will be 0.375 Kelvin per watt. So the problem here is it is not this, no? Meaning this is the total needed resistance, but we only have this per each brick. So we have to divide how many number of bricks do we need. So we can find the number of bricks by dividing 0.375 by 0.08. Oh. So we can solve this again. So divide by 0.08. You can have 4.69. No? So we have 4.69. Or in other words, you don't have a half a brick, no, you don't buy half a brick. So you should use 5 bricks. So you can imagine this one, to attain the 1000 degrees Celsius, you need 5 of this brick A. So what happens is you will multiply this by 5, no? Okay, which is 0.6. So you have already 0.6 meters of this brick. And the temperature of that surface is 1000 degrees Celsius. Okay, so uh, what we can do here in the meanwhile is to actually have this multiply instead, no? So we don't have 4.69, we will use 5, multiply this by 0.08 to actually have the actual resistance, no? Not the minimum, but the actual resistance that we need. So this will be 0.08 times 5, no? So this will be 5 times 0.08, so 0.4. So Kelvin per watt. So this is the minimum. This is the actual that we can have with the discrete values of the bricks, no? So kasi bilang-bilang yung bricks, 1, 2, 3, 5, no? Okay. So we will use this later. So we can imagine we have 0.4. Actually, we don't need it. We don't need this anymore. We already have this. So we can imagine this is now 1000 degrees, no? We can use this 1000 degrees. I mean, it can, I mean, you can check pala, no? Actually, we can check first, no? So to find the temperature again, using this formula, so you have 800, so I won't write the 1 anymore. So 13 minus T2 over 0.4. So you will get a T2, you will get a T2, um, this will be 13 minus 800 times 0.4. So you have 980 degrees. So if this is 980 degrees, then we are good to go, no? We are good to go. It will only have this value. This is the temperature it will reach in a maximum when 800 square meter, sorry, 800 watts per square meter using 5 brick A. So we are good to go. Therefore, we should move with brick B. So brick B should be fully utilized because of its superior resistance, no? And you can solve for brick B. So you can imagine again, this is your circuitry. So you have 3 degrees Celsius, you have, well, I'll just write this down later. So you have 0.4 watt per, actually just the resistance so is Kelvin per watt, no? Well, you can now solve for this one, no? So you have 40 degrees here. You can solve for the resistance needed here, no? Assuming it's still, no? We can still assume that this is 1000 degrees Celsius, if you want. But at least the most correct one is still to use 980 degrees. But anyway, at extreme cases, you can still write 1000 degrees here. So to solve for that, no, so Q is equal to, or QA is equal to T, this will be T2, no? So T2 minus T3 over RB, no? So RB. So the Q here is 800, no? And then 1 as area, 1 square meter. And then T2 is 1000 minus T3. So T3 here is 40 degrees, no? And then divide this by RB. So RB here is 0.35, no? But we will solve for RB first, no? The minimum RB that we need to reach this 40 degrees Celsius. So you can have an answer here to the RB min. So you have, what is the value of this? So you have 1000 minus 40 over 800. So we have 1.2 Kelvin per watt that you need to be able to reach 40 degrees Celsius, no, from 1000 degrees. Well, actually, the best thing to use here is still 980, but I'm just imagining a worst case scenario, no? So what we can do here next is we can solve for the number of brick B that is needed, since the thickness here is only 0.07 and this is the only resistance it has. So we can divide 1.2 to find the number of bricks needed. So 1.2 Kelvin per watt and 0.35. So you can solve this 0.35. How many bricks? Brick B. So you have 3.43, no? So 3.43, in other words, this is about 4 bricks needed. So to reach that RB min, you have to multiply 0.35 by 4, no? Which is about 1.4. So this is the actual value, no? Because you don't have half of a brick, no? You can buy half of a brick and use it. So therefore, in here, as you can see, this will be 4 times 0.07 and that will be 0.28, no? So therefore, we can say already that the brick needed, or the length needed, or the thickness needed is the length of brick A plus the length of brick B. So the length of brick A is 0.6, the length of brick B is 0.28, then therefore this is 0.88. Okay, so this is in meters. So you may also write thickness here, or T, no, small t if you want, but just use L here for this. Okay, so that's it.